All right, this video is to help my students figure out how to do weighted atomic mass averages. So what I have here is a schematic of an atomic mass spectrometer. We're going to pretend that we're going to put a small amount of boron in this syringe, and then we're going to add this syringe, to the mass spectrometer, and we're going to get a mass spectrogram in order for us to figure out the weighted atomic mass average, for the element boron. So I'll hit start. Okay, and this is the graph we get as a result. So relative abundance is on the left side, atomic mass is on the bottom. So there are two isotopes that occur naturally for boron. It's boron 10 and boron 11. Okay, what's the relative amount for isotope 10? Well, if we look at this, it's about maybe 22. So that's its relative abundance is 22. And number 11 looks like it's about 100. So now we're going to calculate the weighted atomic mass average based on this. So if you go to the worksheet provided, we can put both isotope values here. This one would be 10, and this one will be 11. Its relative abundance was 22, and this one was 100. So what's the percent? Well, this one's going to be 22 out of the total of 122. And this one here will be 100 out of the 122 total. So the 122 comes from adding these two together. Now, what about the mass percent contribution? So we're going to take 10 times by 22 divided by 122. And that turns out to be 1.8033. Now we'll take 11 times 100 over 122, and that'll give us 9.016. Okay, when we add both of those together, what you can do then is write the answer down here, and the weighted atomic mass average is going to be 10.82, for that particular those particular isotopes of boron. So that would be something probably pretty close to what you'd find on the periodic table, because all of them on the periodic table are weighted atomic mass averages. So now to try to help you understand what we mean by weighted atomic mass averages, every element on the periodic table has naturally occurring isotopes. Hydrogen has H1, called protium. There's hydrogen 2, deuterium, and hydrogen 3, tritium. Hydrogen 1 has 0 neutrons. Hydrogen 2 has 1 neutron. And hydrogen 3 has 2 neutrons. So an isotope are atoms of the same element, but they have different number of neutrons. When we look at the periodic table, the atomic mass is listed as 1.00797. Okay, why is it such a long decimal out there? Well, it's a weighted atomic mass average of all of the naturally occurring isotopes. Most of hydrogen is in the form of hydrogen 1 with 0 neutrons. Therefore, the mass is closer to hydrogen 1. So we use the mass spectrometer to figure out the relative abundance of each isotope in each of the elements, and then we weight atomic mass averages those together.